Hi everyone. First of all, I'd like to thank Orkide Hoca and Orkun Hoca, as well as Bilal, Erbilcan and Oğuzhan for organizing this beautiful interdisciplinary workshop. And also, it is very nice to have this event in the International Year of Quantum Science and Technology. I don't know if you are aware of the fact that but UNESCO announced that this year will be celebrated as International Year of Quantum Science and Technology. Is there anyone who knows this announcement and celebration?
Yes.
Among the students, there is no. Okay. Actually, the motivation is to create a public and political awareness about quantum science and technology. But today, Orkide Hoca discussed quantum physics, quantum chemistry, but what is quantum science? Let's first start with this discussion, because in the name of this year, it doesn't appear quantum physics, it is quantum science. And quantum physics has many sub-disciplines. Quantum mechanics, in chemistry we call it as first quantization, and quantum field theory, as well as quantum information theory, and foundations of quantum. And each of these sub-disciplines have different kind of perspectives among, for the physical reality. But quantum science is something beyond quantum physics, and it includes quantum chemistry, quantum optics, quantum biology, quantum cosmology, and so on. What does it mean? It means that there are some systems and processes, like chemical systems or biological systems, which obey the rules of quantum physics. And these rules can come from quantum mechanics or quantum field theory. For example, in order to understand quantum chemistry, we need first quantization, quantum mechanics, as well as second quantization, quantum field theory. But also, this name includes technology. Science and technology appear together. Why? Because we started to use quantum nature of systems and processes for some operational purposes. For example, for quantum computation, quantum cryptology, quantum communication, and quantum sensing and methodology. As an example, this laptop is a quantum device. You cannot explain its working principle without quantum mechanics. It includes transistor. How many of you know what is a transistor?
You even know the tubes.
You can imagine the transistor something like a switch. It has two configurations, 0 and 1. And in order to change one configuration to another, you need to employ quantum tunneling. Because otherwise, it is not possible to have such rapid fast laptops. But we don't call this laptop as a quantum computer. Why? In quantum computer, we don't only have a control on the quantum systems, we also have a control on its quantums. And the underlying framework is called quantum information theory. And the main part comes from the mathematical framework called quantum resource theories. And what I will aim today is that I will try to reconsider quantum chemistry from the perspective of this quantum resource theories. So, in addition to first and second quantization, we will introduce some other perspectives. And we will start with the phenomenon of chemical bonding. Before starting, let me ask another question. Do you know what is quantum superposition? What can you say about quantum superposition? Yes. Okay.
It's the Prof. It excites the electron. And the electron has to go to the reaction center. For the electron go to the reaction center, it's nearly 100 C. It has no always. For that, it don't have to be in all places. And it have to be in superposition. Like if you say like that.
I think it's a nice introduction for us. First of all, we need some observable states, and then quantum superposition corresponds to the coexistence or simultaneous existence of these observables. And Orkide Hoca showed you many difficult or not difficult mathematical formulas about quantum chemistry, but at the end, you run a program and it produces something like that, some balls and sticks. And this depiction simplifies the chemical reality a lot. But you learned chemical bonding by using many such depictions. Another example is this one. Do you remember this depiction from high school? Then I have a question regarding this depiction. In this depiction, what is the aim? What is the aim? We have two electrons and they are shared between two nuclei, and we call this process as chemical covalent bond. But let's make it more simple and remove one of the electrons. Then we have a single electron covalent bond. Then my question: what is the position or location of the electron? Should we locate the electron in between the two nuclei? Any idea? Yes, you are right. There is no definite location of the electron, but let's first try to impose such location. Assume that both electron and the two nuclei are classical charged particles. And here, assume the vertical axis is the energy, and horizontal axis is the reaction coordinate. The first point corresponds to the presence of the electron inside the first hydrogen atom, let's say the left hydrogen atom. And the second one means that electron resides in the second or right hydrogen. If you enforce the initial electron from left to right, then this electron feels such a potential. If you consider this potential, the middle point has a higher energy. Higher energy means that there is an instability. But what we expect to see in a chemical bonding is an increase in this stability. So classical perspective is not sufficient to understand the stability of chemical bonding. But what happens? The real thing is the coexistence of these two states. We have to take the superposition of these two structures, which means that electron should exist in both nuclei at the same time. And we call this coexistence as superposition. And superposition is what lowers the energy and provides the stability for chemical bond. But now let's return back to your point. Originally, we have an orbital in the first atom, and this orbital means that electron has a fixed energy. But when you fix the energy, there is an uncertainty in the position. Why? Because energy eigenstates are superposition of position states. And what happens in the case of the formation of the molecule? Then these orbitals are overlapped. This overlap allows the delocalization to extend to both volumes. So now electrons delocalize over the whole molecule as a result of the superposition. And in this way, you can explain how the probability to find the electron in the middle point increases. Because in the real bonding phenomena, there is a high probability in the middle point. And the situation is the same for the double electron bond. This time, we assign different spins to the electrons. But again, for the pure covalent bond, we need to write a superposition state. And For the all lectures, I will use this notation for the superposition. These two-ended arrows corresponds to superposition phenomena. And let's have a look at more complicated molecules. For example, benzene. In benzene, you know, these second lines represent pi bonds, and we can distribute the pi bonds as in the case in the left or right, and both structures have the same energy. But if you try to calculate the ground state of the benzene, then again, you need to take the superposition of these two structures. What does it mean? For inside each pi bond, we have 2 pi electrons. So we have 6 pi electrons in this case, and we have 6 centers. Each corner corresponds to carbon atoms. So 6 electrons then equalize over 6 centers. So this is the multi-delocalization theorem. Let's have a look at another example. I think you are familiar with this structure. This is the primary structure of proteins. We have a backbone, carbon, carbon, and nitrogen backbone. And what determines the secondary structure is this dihedral angles, phi and psi, as well as the partial charges appear on the oxygen and nitrogen. But how we can explain the presence of partial charges? Is it possible to divide electrons into smaller units?
Well,
Density means probability, actually. Once again, it is related with the superposition. Here, we have 2 different structures. In one of them, oxygen and carbon shares the double bond, and the alternating structure, carbon and nitrogen shares this double bond. When you take the superposition, you end up with partial double bond, and these partial double bonds explain the appearance of these solid regions by the way. Once again, without using these solid regions, you cannot explain the secondary structure of proteins. So, in order to move from primary structure to secondary structure, we have to employ the superposition principle. Is there anyone who cannot understand why partial charges are related with superposition? How we can measure superposition? Do you have any idea? Or what happens if we try to perform a measurement on a system that exists in the superposition state? No, assume that we have an ability to design a device which can distinguish these two structures. For example, we can locate the position of the electrodes. I don't know for this structure, but for the benzene case, we know that both structures have the same energy. So there's a possibility to have the same energy for the molecules. In the superposition, we say that there are different observable states that coexist. Whenever you try to perform a measurement,
when we measure the superposition purposes, we only see one state.
Whenever you perform a measurement, in order to get the information, then you end up with one of the terms in the superposition. You lose that. But remember the wave function from TBAE. Wave function is nothing but a probability amplitude. It's a complex number at a given position in space. When you take its modulus square, it gives the probability or density. So inside the superposition, I didn't write, but there are some probability amplitudes. And this determines the probabilities for the measurement statistics. So, for example, for this oxygen, you can say that in this case we have one electron, one unpaired electron, but in this case we don't have any unpaired electron. Assume the probability for this term is P. So P times 0 plus 1 minus P times 1 can explain this partial charge. Okay. Once again, let's focus on this covalent bond. In the previous slides, I said that we are talking about pure covalent bonds. Do you know what I mean? Whenever we have a real chemical bond between two atoms, X and Y, again, we have to go beyond the pure covalence description. There is a superposition, and one term corresponds to pure covalent bond, the share of the electrons in the form of superposition. But also, this superposition includes some ionic terms. And as a result, each real bond has an ionic character with a particular percentage. And this percentage is determined by the probability once again. But we can enlarge the description, consider a hydrogen bond. In the hydrogen bonding, what we know about hydrogen bonds, they're classical and weak interactions. But again, the state that describes the hydrogen bond can be written as a superposition. We will talk about it in more detail in the second lecture, if I remember correctly. And this superposition includes both this term and this term. Let's have a look at that. In one of the terms, hydrogen is bonded to the first atom, but in the second term, it belongs to the second.
How do we differentiate between ionic bond and covalent bond?
Let me use the perspective of Linus Pauling. By the way, it is one of my heroes in science. It is one of the founders of quantum chemistry. And what he says in his Nobel lecture is that there is no real boundary between the bonds. These are the abstractions that we investigate. But in reality, in the chemical reality, we cannot classify bonds as covalent bonds, ionic bonds, or metallic bonds. All the boundaries are artificial. And let's return back to this hydrogen bonding. As you see, in one term, hydrogen makes a covalent bond with X1, but it makes the same bond with X2 in the second term. So if you are allowed to perform a measurement to locate the position of proton, then you have both probabilities. And for example, consider the DNA double-stranded DNA. But let's say stabilize the interactions between two strands is the hydrogen bonds. Assume that just before the splitting of the two strands in the replication process, a measurement happens and proton resides in the wrong place. Do you know what can happen? Mutations, DNA mutations. So superpositions in chemistry is related with biological function of the molecules. In the previous slide, we discussed protein folding. And structure of the protein depends on the superposition and also determines the function of the protein. Not in all cases, but in many cases. And do you know what is interference? Interference is an indicator of superposition. When you have superposition, you can design some experiments, like the double-slit experiment that I showed in the cartoon. And by using some real molecules, for example, gramicidin is a small antibiotic. By using such molecules, we can create interference fringes. which means that quantum superposition extend over the whole molecule in this case. If you don't have any question, then I will compare the two theories that we have in chemistry. One is valence bond theory. We use it in order to explain the geometry of the molecules. And the main ingredient is hybridization. Do you know what is the hybridization? What are the hybrid orbitals? Any idea? Hybrid orbitals, here 2s and 2p are the atomic orbitals of the hard orbital. And when you talk about sp3, it means that these hybrid orbitals are superposition of p and s orbitals. So they are superposition of atomic orbitals belonging to the same atom. And in valence bond theory, electrons fills these hybrid orbitals first, and then you can explain the molecular geometry. For example, even we can explain the geometry of water without this hybridization. And on the other hand, we have molecular orbital theory. This time our motivation is to calculate energies of the molecules. And instead of hybrid orbitals, we have molecular orbitals. And these orbitals are again superposition of atomic orbitals. But this time, these superpositions include atomic orbitals from different atoms. And electrons fill these molecular orbitals, then we can explain the energy. Each molecular orbital has a different energy. And in the valence bond theory, we have valence bond structures, and in the molecular orbital theory, we have configurations, electronic configurations. Let's say these are the most stable structures or configurations for a given molecule. But once again, it is not sufficient to explain the real geometry of or real energy of molecules. In the valence bond theory, you have to consider many possible valence bond structures and take these superpositions. For example, do you know the geometry of benzene? Do you know the bond lengths? All bond lengths are equal in benzene. If you want to explain this, you have to include many terms in this superposition. And similarly, by the way, we call this process as resonance. Resonance is nothing but quantum superposition. Similarly, in molecular orbital theory, this ground state configuration refers to the Hartree-Fock configuration that Orchid mentioned. And you can consider excitations from this ground state, and the real energies of the molecules requires the superposition of these different configurations. We call it as configuration interaction. And both theories have some different predictions, but if you consider all the superpositions, all the terms in this superposition, or all the configurations in this superposition, then it corresponds to full CI limit, and in this limit, two theories become equivalent. Their predictions become identical. So, both conceptually and numerically we need quantum superposition. Otherwise, we cannot explain chemical bonding. And let me also introduce some mathematical notations to describe these electronic states. In the second quantization, we have orbitals. Orbitals are called as Fermionic modes for the physicists. Electrons fills these orbitals, and the movement of one electron from one orbital to another is described by annihilation and creation operators. Here, F mu destroys the electron in the orbital mu, and F Dagger mu is the creation operator. It creates an electron inside this orbital. So in order to explain the movement of the or excitation of the electron, first we will destroy the electron in one place and then we will decorate it in another, inside another orbit. And we can write down the Hartree-Fock ground state in this way. Assume that 2n is the number of orbitals. Why I use 2n? Because each orbital includes two modes, spin up and spin down modes, or alpha spin or beta spin modes. And assume I is the number of electrons. So we have to create an I electrons. This is the vacuum state. You apply these operations to the vacuum states and then create the electrons one by one. But there is a particular point we have to be careful. Here, as you see, there is a relation between annihilation and creation operators for the same orbit. What does it mean? Do you know these curly brackets? What does it mean? Anti-commutation. Anti-commutation. Once again, Orbital mentioned about this. It means that you will multiply these two operations in the reverse orders and then take the summation. The summation should be this one. This is, let's say, Kronecker delta, mu and nu. It is 0 whenever these two indices are different, and it is 1 whenever they are identical. What it means? It means that this anti-commutation relations ensures or provides the anti-symmetrization that we need. And this vanishing anti-commutation, by the way, is related with the fact that whenever you change the position of two operations here, you will end up with a -1 phase. And this phase appears as a result of this relation. And in this way, we can explain Pauli exclusion principle. For the physicist, here you see an occupation number vector, but here we do not connect the subsystems by using tensor. Standard quantum mechanics tensor product is used to enlarge the Hilbert space, but here, as a result of the hybridization, we need wedge product. What does it mean? It is the antisymmetrized tensor product. Again, whenever you change the position of the electrons at two different orbitals, you end up with a -1 in front of the state. What about the state of the correlated electron? In the Hartree-Fock, remember the previous lecture of Orbital, we neglect the correlations or interactions between the electrons. And each electron feels the effective potential of the others. And then you have n-coupled differential equation, all of them. And we create the Hartree-Fock orbitals in this way. But different Hartree-Fock configurations are orthogonal to each other. And they are linearly independent, which means that we can span the whole Hilbert space by using them. They constitute a proper basis. And any superposition of these bases can represent the real ground state of the molecule. Here, when we apply here, this is the single excitation operators. We destroy the electron at the orbital I, and then create another electron in the orbital A. So single excitations can be calculated in this way. These are double excitations. You can consider higher order excitations, and in this way we can end up with a correlated state. But by the way, this structure is called as computation interaction method. It is an expensive method. Its computational cost is not low, but I will give some simplifications that we can use. Another method to construct this correlated state is coupled cluster. Is there anyone who knows or who heard coupled cluster theory before? No. Both configuration interaction and coupled cluster are post-Hartree operators, which means that their reference state is the Hartree state, but then they use perturbation theory to, let's say, reconstruct the neglected correlations between the electrons. Configuration interaction is not size extensive, which means that if you consider two molecules, or for example, two water molecules, which are not interacting, then their energy is not additive in the configuration interaction. If you don't consider the full CI, which means that full excitations. Full excitations is expensive. So whenever you truncate this equation, you end up with some problems. And coupled cluster solves this problem. Coupled cluster, you obtain the same excitations by using some exponential of the same operators. And then the form of the state becomes a product, and it becomes size extensive. And remember the density that Orbital mentioned. This state is called as state vector in quantum mechanics, but it is not sufficient to describe all possible physical states in quantum. We need to have to construct something called density matrix. Density matrix is constructed by the outer product of the state vector. You can represent it as a matrix. I will show it. And its diagonal elements correspond to densities that Orbital mentioned. Densities are the diagonal elements, and also they will correspond to probabilities. So in the density functional theory or in any other density-based theory, you neglect the off-diagonals. And we will see that off-diagonals are related with the correlations. One way that we have to decrease the computational cost of these calculations is tensor network representation. Do you know what is a tensor? Who knows what is a tensor? Dot is a tensor with rank 0. Vector is a tensor with rank 1. Matrix is a tensor of rank 2. Is it something reasonable for you? Is it something that you can imagine? You can design any tensor with an arbitrary rank. And in the correlated electronic state, we have some superpositions. As you say, it includes many indices here, J1, J2, and Jn. So you can imagine it as a n-rank tensor. And whenever we have a high-rank tensor, we can decompose it as the product of lower rank tensors. In this way, we can, here, for example, let me show one example. The open legs corresponds to the original rank. So here the rank is 5. But you can imagine all the closed ranks as the matrix product. So you can multiply rank 2 elements or matrices to represent these rank 5 objects. In this way, you can reduce the computational complexity. Another idea is neural network representation. This time, you can take this wave function or probability amplitude, and you can imagine it as a n-variable function. And what we know in machine learning is that whenever we have a multivariable function, we can write it as a unification of two functions. In this way, you can create two different layers. So you can take these numbers and convert them into the x in the neural network. But this is something different than the usage of neural networks in other scientific fields. Here, we don't use it as a black box. Here, we use it to represent some numbers. And then once again, we optimize the structure which corresponds to the variational solution of the energy. And one more thing that I need to emphasize, I compare the configuration interaction and coupled cluster. In the configuration interaction, you calculate these numbers or probability amplitudes by using a variational principle, but coupled cluster is not a variational approach. It is something else. Okay? If you don't have any question, then I will focus on the meaning of quantum strategy.
One which you learn that created. For example, I have a data of 3. So how much we learn I will take it further for my data. Here we see 3x in the 5 terms.
Yes.
Is there any ratio or correlation?
These structures correspond to different architectures in neural networks. Depending on the, let's say, properties of your molecular system, you can choose one of them as a better answer. And the number of the neurons inside each layer then can be calculated by the given formulas. For each architecture, the number can be different.
I'm just a little bit confused about the numbers. It depends on sample size or molecule shape.
It depends on the correlations between the electrons inside this molecule. So whenever you get high correlations, you need a more complicated architecture to represent it. But for example, in aquaculture, light absorption is important. For example, for the macro algae. If I remember correctly, by this method, you can calculate electric structure of the whole Prof.
For agriculture, I understand that beginning is the last term, same, so you can put it in the middle, something that is behind.
Nice. Any other question? Let me also double check. Now, let's focus on the physical meaning of quantum superposition. Again, I will use a depiction. Here, the balls will represent the systems and arrows correspond to physical states. Whenever we have a right angle, it means that these states are distinguishable, perfect distribution. And quantum superposition doesn't require any orthogonality between the states. But whenever you take the superposition of orthogonal states, then we call it as quantum coherence. So quantum coherence is a special case of quantum superposition. And for example, assume that this state of our system is this one. So with some probability amplitude, its color is red, for example, but with another amplitude, its color is blue. If you perform a measurement, then to end up with the color red is determined by the probability of modulus square of this complex number. And when we construct the density matrix, you can see these numbers in the diagonal. So here, as you see, diagonal numbers corresponds to probabilities. But off-diagonal numbers are the indicators of quantum superposition. For example, by using a measurement, we cannot access them. It means that before the measurement, we know that the state is this one, so we have the complete knowledge about the system. But whenever we perform a measurement, we lose some of the information because it turns out to be a probabilistic mixture. Whenever we have probabilities, it means that there is an uncertainty. And uncertainty reflects the lack of information. So, performation of the measurements reduce the information content, which is carried by the superposition. So, quantum superposition is a manifestation of quantum information. But this is an interesting quantity. We cannot extract this off-diagonal numbers, but we can design some operations which can change or which can allow the interactions between diagonal and off-diagonal numbers. For example, all the power of quantum computation comes from this element. Another important point, we can change the basis of the measurement. Here, our question was that is the color is red or blue? We can change the question and ask is the color is purple or not? Then the same density matrix has a different representation. Here, probabilities are different, and also off-diagonals are different. This provides an interesting contextuality to quantum superposition. This is what makes quantum computers more powerful than classical computers. We can extract this contextuality and use it for our operational purposes. And I have to introduce one more notion, correlation. Correlation has different meanings in different disciplines. For example, in condensed matter, whenever two states, for example, whenever two spins are identical, we call it as correlated. But in quantum information theory, we will not consider any correlations between them. In order to have any correlation, we need some probabilistic interpretation. If the system exists if the both systems exist in the blue state with some probability, and if their color is red with another probability, then we can discuss the notion of correlations. So whenever you have any information on one subsystem, then you can guess the state of the other system. So correlation is shared information. So if quantum coherence is a manifestation of information, then shared quantum coherence also corresponds to correlations. And we call such correlations as quantum entanglement and quantum discord. This kind of correlations are non-local. What it means that on one hand, you can perform a local operation on one subsystem, but you affect the whole system. Whenever you have such relations, you can say that quantum correlations are present, but note that this doesn't allow us to have communications faster than light. So we cannot violate the causality. So it means that assume I have two electrons and they share some correlations and they are inside the laboratories. An operation on this electron affects the other, but an observer in this laboratory cannot understand this effect. This effect cannot be extracted locally. It becomes a resource only if we have a global access to the whole system. And there are many fields in which we utilize superposition, coherence, or correlations as a resource. One example is quantum computation. Let me show you an example. Here you will see an algorithm, and the aim of this algorithm is to discriminate between even and odd permutations. This algorithm is used by a three-level system, and initially it requires this superposition. whenever you can create this superposition, you can perfectly discriminate the even and odd permutations. And there is no classical algorithm which can work better than this algorithm. And this is the simplest algorithm that we know. And the inventor is something that we know is a cross of dreams. Another algorithm, let me show another algorithm, Grover algorithm or quantum search algorithm. In this algorithm, you have different items, you put them in a black box, then choose a random item, and your job is to find the particular item among the others. This algorithm, if you have 4 items, then two-level systems are sufficient, and the requirement is this initial superposition. As you see, we have a uniform probability amplitudes here, but in the previous example, the amplitudes are not uniform. So for each computational purpose, we have to construct a different superposition. So shape of the superposition determines its functionality. And remember, inside chemical bonds, we have superpositions that determines the structure, which is related with the function of the molecule. Another application of these resources, how many of you know Kaptan Kök? Only a few people.
1970s.
But it may be interesting for young people as well, I think. Let me show you quantum teleportation protocol. In quantum teleportation, first of all, we have an unknown state, the state of Kaptan Kök. Then we have an entangled pair of molecules, and what we will do is that we send one of the entangled particles to Kaptan Kök. Then Kök will perform some measurements on both of the molecules. Then remember, the other people, Spark, cannot understand if Kaptan Kök manipulates entanglements. So Kaptan Kök have a classical communication with Spark and gives the measurement outputs. Then by using these outputs, Spark can create this unknown state on another molecule. So we can send information from one point in space to another by consuming entanglements. We consume entanglement. It is a resource. Whenever we have a maximum entanglement, then we can finish this protocol with a unit success. Whenever the amount of entanglement decreases, then the success probability decreases as well. And the first experiments were done in the beginning of the 90s, but today we are able to perform teleportation from ground to satellites. And then we can use these resources for communication protocols. Assume that we have 2 different pair of entangled molecules. We can send them one molecule from one pair to a user and send the one molecule of the other pair to another user. Then assume that at the center we have the molecules 1 and 4. If we manipulate 1 and 4, then we can create entanglement between 2 and 3. We can swap the entanglement initially, 1 and 2 entangled, and also 3 and 4 entangled. We distribute them in a way that 2 and 3 now are in different places, are inside the laboratories. But by using some operations on 1 and 4, we can create entanglement between molecules that have not been interacted previously. In this way, we can build up counting patterns, or we can construct secure cryptology protocol. But let me show, I think, a stronger manifestation of these resources. What we know about the second law of thermodynamics is that heat should flow from hot to cold. Here you see an experiment. This experiment was done by using chloroform molecules. And the system of interest is the nuclear spin of the carbon and hydrogen atoms. And this is an NMR setup. It is isolated from the environment. And what they show is that whenever there is an initial correlation between the nuclear spins, you can end up with a heat flow from cold body to hot one. Let's have a look at this example. Here, I think, let's consider the orange cases. One spin has an energy 1.1, let's say. The other one is more closer to 1, so energy is higher here, which means that its temperature is higher. And as you see during the interaction, its energy increases. So its temperature increases. And here mutual information quantifies the correlations. At the same time, correlations decreases. So by decreasing correlations, we can create anomalous heat flow. So they are real physical resources like electricity and energy. And we can return back to the chemical bonding phenomenon. If superpositions arise as a result of electron deregulation in chemical bonds, then is there a possibility to utilize these resulting correlations for some operational purposes? In order to answer this question, we need to discuss something more. Let me first compare the first and second quantization pictures. In the first quantization picture, we have particles. Particles are the main atom. In the second quantization, we have orbitals or Fermionic. Now assume that we have two electrons which are delocalized at two sites. In the particle mode, you can write down the determinant, static determinant or wave function in this way. And this includes some entanglements. But if we move on to the mode picture, if you move on to the, let's say, second quantization, then you see that at each site we have a single electron. And it's a product state. Whenever we have a product, there is no correlations. For example, consider the two electrons inside the same orbit. Their state is usually singlet state. I think we are familiar with singlet states. And in the singlet state, you have a superposition. They are correlated. But this correlation, this entanglement, is not useful for us. Why? These electrons are indistinguishable. We cannot distinguish them. As a result, we cannot extract the correlations between them. This is why the entanglement disappears here. So, second quantization picture is more suitable to investigate correlations. Let me skip the other examples. And particle picture has some other problems. Let me show one of them. Let me skip it and show something else. Once again, assume that we have two orbitals, A and B, and have a single electron. Is it possible to have such a superposition state? What do you think? We have a single electron. Is it possible to have, for the molecule to have this superposition state? Here, in the first term, there is no electron. But electron number, particle number is 1 in the second term. So particle number is not conserved in this example. What happens if we allow to have such superpositions? Here, A and A dagger are the creation and annihilation operators inside the first orbital. Their sum corresponds to the position operation, by the way. If you calculate the expected value of position, you end up with 1. Then assume we apply a local operation on the other orbital. If you do this, you convert the state into this one. And if you recalculate the same expectation value, it becomes -1. If you allow this superposition, then it means that local operations can be detected in the other systems, and it allows the violation of the causality. So we cannot allow the presence of such superpositions, and they are called as superselection. Whenever you calculate the ground state of a molecule, the whole molecule state obeys the superselection rule, both particle and parity. They are the same for all the terms. But what we need in quantum information is that we have to construct the reduced state of subsystems. For example, in the benzene cycle, you can take 2 carbon atoms and discuss the correlations between them. Whenever you calculate them, you can end up with such problematic superpositions. So calculation of quantum entanglements inside orbitals is something more restricted. Let me move on this part, starting here. I can say one important thing about the utilization of quantum computers for the purpose of quantum chemistry. Our quantum computers are based on qubits. Qubits are distinguishable particles. And our electrons or Fermionic modes are indistinguishable systems. We can move from one description to another by using some transformation called, for example, Jordan-Lignite transformation. You can map the global state of the fermions to a global state of electrons, and then solve your problem in the quantum computer. But if you take the reduced states and apply the same transformation, you don't end up with an equality. So local properties cannot be preserved by these transformations. So there are important restrictions of quantum computers in the field of quantum chemistry. Let me skip these parts and show you some examples. Here, for example, here we have the most simple molecule that we know, water molecule. In water molecule, here the numbers are the Hartree-Fock orbitals. I is the total correlations between the orbitals. These are pairwise correlations. And C means classical correlations. D is quantum discord. E is quantum entanglements. As you see, even for these simple molecules, we have very complicated correlation networks. And these correlation networks change during chemical reactions. Let me give you an example from biology. Do you know photoisomerization? It is the reaction that takes place during the vision perception. We have a protein called rhodopsin. Rhodopsin includes the opsin protein and retinal subunit. Here you see the retinal. This is the active part of the molecule. It has 2 configurations, cis and trans. Whenever it absorbs the light, there is a conversion. First of all, you excite the molecule, and then during the relaxation, there is a chance for the molecule to change its structure. And but this is a probabilistic process. And do you know the success probability of our vision? Do you know the assume that I send you 10 different photos. Do you know how many of you do the perceive value? Something like 7. So we have a high success probability. For the remaining probabilities, the molecule returns back its original shape. Now I will show you a paper. In this paper, they, I think this was the team led by Massimo Orbital. They built a quantum chemistry package only for RODOPS. It works only for RODOPS. It takes the whole RODOPS in molecule. Only the retinal part is described by the quantum chemistry. The other parts are modeled by molecular dynamics simulations, but they didn't apply Born-Oppenheim approximation. So configuration can interact with the electronic structure. In this way, you can explain the conversion from cis to trans. But when they follow the single trajectories, they cannot understand what is the thing that drives the molecule in the forward direction or the backward direction. They cannot find anything that can explain this random process. When you consider the distribution of the orbital correlations, then you can get something about this process. Some particular distributions can drive the molecule to the trans configuration, but some others do not allow it, and the molecule returns back its initial configuration. Now, let me stop the first lecture here. Sorry if I don't use the time effectively. Do you have any question?
Is there any kind of intent, like similar to the populations statistics process?
You mean the magnitude of the entanglement?
Is there kind of age, like between 0?
For two-level systems, the maximum amount of entanglement is 1. But when you increase the dimension of your subsystems, then this upper bound increases as well. For the molecules, so it depends on the structure, the number of the electrons, the number of the occupied and vacant orbitals. All of them determines the upper in the molecule.
So we can see some entanglement results like 2, 3, 4.
Yes.
Okay.
By the way, there is a nice connection between bond order and entanglement, orbital entanglement. So this kind of abstract notions can be utilized to understand some chemical concepts in more detail. Any other question? Okay, then let me stop. I think.